Okay, we're back. This is part 2 of a video about Euler solutions to differential equations. My name is Eric. We're working exercises off a page I wrote, and it's called Euler Solutions to Differential Equations. Part B, technology problems, actually is going to start off with a classic separable differential equation. We're going to solve it using techniques of algebra and antiderivative. So it's not a technology problem. The technology comes in later. What we're going to do is we're going to get an exact closed solution to this differential equation subject to this condition. We're then going to evaluate that function at x equals 196 and come up with a y number. Then we'll attempt to do it using the Euler solution and some technology, actually a spreadsheet. That'll give us a way to compare and see how good Euler solution is in this particular case. Let's get started. So we want to solve this differential equation. One of the things you might do to get this started is rewrite y prime as dy dx. After all, if you're going to solve a differential equation, you need some differentials. Then you want to separate it. Now, when it's separated, all the x's and dx's will be on one side, y's and dy's will be on the other. And so the first thing I notice is I've got all sorts of variables mixed together here, and this dx should probably go away. That's achieved by doing a multiplication with dx on the left and on the right. After canceling, we have an improvement. And yet we still have a y differential mixed with an x variable. So we want the square root of x to go away, and of course, to do that, you just divide. That's going to look like this. And now it's separated, and it's ready for us to do antiderivatives. Just before you do that, my students find it helpful to multiply by 1 here. It'll help them visualize what the antiderivative of dy is. And on this side, rewrite the square root of x as a half power of x, and then bring it up to the numerator as x to the negative 1/2 power. Like that. Okay? Now, the derivative of x with respect to x is 1. The derivative of y with respect to y is 1. And so the antiderivative of 1 up to a constant should be y. And on this side, antiderivative of x to the negative 1/2 power, of course, you're just going to add 1 to that exponent. So negative 1/2 plus 1 gets you to positive 1/2. But then you have to divide this coefficient by the result of that raised exponent. And then, of course, add a constant, either here or both. I always put it on the right, A, B, or C, whatever makes you happy. Now, of course, 0.5 divided by 1/2 is 1. Another way to write x to the 1/2 is square root x. So we come up with y equals square root of x plus b. That's called a general solution. Any single function that has a derivative that behaves this way or meets this, the requirements of this equation, well, that function will always look like this. And there's built into these things, of course, because there's lots of different constants. We have the privilege of knowing what this constant is by using this initial condition. So we just plug those in. And pretty clearly, b equals negative 1. Now, the goal is not to figure out what b is. The goal is to write y as a closed calculation of x. So just take this negative 1 back up to here, and you have y equals the square root of x minus 1. Now, when you use this to compute values for this function f, they're not approximations. They are rock solid, completely accurate, and when you can get an antiderivative, when you can get this formula for y, this is the way you should go. Our next job here is to compute f of 196. And that would be just plugging 196 into that. So f of 196 equals the square root of 196 minus 1. That's 14 minus 1, and the answer is 13. Okay, we're going to put that off to the side, keep track of it, because Euler is not going to give us 13. Euler's solution of this differential equation is going to give us something close to 13. Okay, I'm going to keep this video going and show you that technological component I talked about just a minute ago. Let me erase this, do a little scrolling, and then change windows over to a spreadsheet. So we have two things to do here, and I'm going to make this go away. We want to approximate f of 196 using the Euler solution, and it recommends Microsoft Excel. You can do this on Google Sheets too. I've done it both ways. The steps are the same, the logic's the same, the syntax is the same. So you can do this on a Chromebook, for example. We're supposed to do 3 of these with these 3 different steps. So delta x equals 0.5 on the one hand, and then delta x equals 0.1, and finally delta x equals 0.05. Now, one of the reasons we want to use technology for this is, do we remember what the initial condition was? It was f of 25 equals 4. And we're going to pretend for a minute that we didn't have a way to get to 13, and that we're going to approximate f of 196 with the Euler solution. It is a long way from 25 to 196. Turns out that's 171 units. So if you did an Euler solution in steps of 1 unit, like if you did delta x equals 1, it would take 171 steps to get there. With this step, it's going to be double that. What is that, 342 steps? So there's no way you want to do this with pencil and paper. And I doubt Leonard Euler would have wanted to do this with pencil and paper himself. Okay, if you haven't used a spreadsheet before, I think you're in for a real treat. And because we're having to do this for 3 different steps, I'm going to show you the deluxe version. Okay? Hopefully you can still hear me over there. Here is a Microsoft Excel worksheet, I guess you'd call it. I've got it on a very large font so that you can see it way out there. That's not necessary for you, but what I would recommend is to get on the divider between cells A and B and click and drag that off to the right so you get these nice wide cells that will accommodate a lot of decimal places. Okay, cell A1, type 25. Cell B1, type 4, the initial condition. And then somewhere over here, maybe in like F1, click on the Formulas tab, go to Define Name, and in this little box, we're just going to give this the name K. That's all you have to do other than to say, okay. Then come up here and click F1 and type 0.5. Now I'm going to put something down here just for demonstration purposes, and then I'm going to throw it away. If you go to this cell, or any cell, and type equals K, you see how the K turned blue? And suddenly this cell, F1, is surrounded by blue. When I hit enter, I get a copy of the K value. And it's not just a copy, it is responsive to any change I make. So for example, if I change this to 0.1 and hit enter, I see that change reappear here. Back to 0.5, delete this cell because you're not going to need it. And now let's set the Euler thing up, okay? I will set this up exactly the way I did the worksheet in the last video. I'll put a new x here. And the best way I know to do that is to type equals, click cell A1, and type plus K. This time it turned red, but you can see it's still referencing the k value over here. If it says 25.5, did right. If not, rewind the video and see what mistake you made. On the worksheet, I always type the calculation for the new y over here. Let me come up and scribble a few things on the board. Remember that for this problem, we had a derivative that looked like this, or a differential equation. Okay, if you solve this for y prime by dividing by root x, you get this. And you're going to need to know that because remember, for the Euler solution, the new y is supposed to be a representation of the old y value plus y prime times the step. Okay, what I actually put in these cells is not going to look anything like this. For example, the y old is found back here. So what I'm going to put in the cell will say equals B1. Y prime is supposed to look like this. So I'll type 0.5 divide by, and then for Excel and also for Google Sheets, you're going to want to write SQRT. That's how you do a square root. Now you need to put something in here for the old x, which is back here in cell A1. So you type A1. And finally, so I've done this and that. All this expression here is y prime multiplied by delta x, which is that k value up here. Okay, sorry it's a little disorganized looking, but everything from here to here, including the equal sign, is going to get typed in there. And then I'll come back and erase it. So, equals the old y plus 0.5 divided by SQRT, open parenthesis, the old x, multiplied by the step, that's asterisk k. You can pause the video if you need a minute, but I'm going to keep moving. I hit enter, and if it says 4.05, you probably did it right. Now, you remember on the worksheet what we did next? We said, hey, this is a new y. We're going to transfer it down next to our new x right here. So the way you do that is you just type equals and click on C1. Enter. And then you're going to want to have the calculation that was here repeated here. If you're going to type it by hand, then you have to switch this to B2 and switch this to A2. You can do that, but an easier way to do it is just to click on this cell. And right now I see my cursor, I guess you call it. It looks like a Red Cross first aid cross. But if you hover over the lower right corner, it turns into what appears to be more of a plus sign. So do that, not with the arrows on it, not that one, this one. Click, hold, and drag down one cell. And release. Now if it says that, you're doing it right. Okay, all the hard part is about over. Now all we have to do is something tedious. And just try to imagine doing this with pencil and paper and even a calculator. It would probably take you 45 minutes, and you'd probably make some mistakes along the way. We're going to select all three of these, and then we're going to do that click, hold, and drag trick on the lower right corner of that cell. That looks like this. Excuse me. Click, hold, drag, release. Hover. Okay. First cross. First aid red cross sign turns into a skinny plus sign. Click, hold, and drag down. And let go. Let's drag a little farther. let's drag all the way to 36. Okay. What is the square root of 36? Because remember, when we solved this differential equation, we came up with a closed formula for f of x, and it was f of x equals the square root of x minus 1. As in, the square root of 25 minus 1 is 4. Well, the square root of 36 is 6 minus 1 is 5. But this is the Euler solution that we're getting using a step of 0.5. Now, we have to do a lot more dragging and scrolling to get all the way to 196. So let's give that a shot. We went way too far, but that's okay, because in a minute you're going to have to go farther than that. I came up with the Euler approximation for 196 as y equals 13.01611. So let's write that down. Here's the Euler approximation with this step. F of 196 is approximately equal to 13.01611. Okay. Now, I'm not going to do the 0.1 and the 0.05 for you, but I will tell you this. If you go back to the top of the page, several hundred cells up, and change the k value to 0.1 in cell F1 for me, and hit enter, I don't know if you noticed, but everything down here has just changed. Something else has changed. You're going to have to go 4 times as far before you get to 196. So far I've gone to here, and I'm nowhere near 196. No problem. Select these 3 cells, grab the lower right corner, and just keep dragging. I'm not even doing 100 yet. Well, I don't want to spoil your fun. I'm going to let you do this. What I want to do right now is talk about how to do percent error. We're going to do error and percent error for the case of this Euler approximation. Okay, now we know that the actual y value associated with this x is 13, because we had the formula, and we were able to do that. This is the Euler approximation with this step. It looks pretty good, doesn't it? It's close to 13. Now, how close? Well, I think you can answer that without me explaining that error equals the absolute value of the correct number minus the approximation. And I don't care which way you subtract, because we're going to take the absolute value of it anyway. If you do this backwards and get a negative, so what? Take the absolute value. We don't care if it's positive or negative. All right, here's the actual function value. Here's the approximation. They're obviously this far apart. So the error equals 0.01611. Now, you may be satisfied that that's a really good approximation just by noticing that the error is smaller than 0.02. However, whenever you look at error and try to make a judgment about whether it's good error or bad error, you need to scale it. For example, if I tell you that I was aiming at a target and I missed it by 12 inches, and then I ask you, was that good or bad? I think you're going to want some more context. So let me tell you what I was doing. I was at a basketball game, And they had a contest where if you could throw the ball all the way down the court, a full court shot, to make a basket, you'd win a new car. This didn't really happen, I'm making this up. But imagine, I throw the ball all the way down the court and I miss the rim by 6 inches. There would be gasping and groaning because everybody who had witnessed it would say, man, you were close. 6 inches. On the other hand, let's suppose I'm chasing a fly around the kitchen with a fly swatter, and he's resting on the countertop, and I'm standing 2 feet away from him, and I try to smack him, but I miss by 6 inches. That's pretty pathetic, okay? You don't want to miss by 6 inches when you're trying to swat a fly with a fly swatter. All right, that was silly, but you get the point. The size of a miss or an error can only be judged as, hey, pretty good or not so great, if you have a way of scaling it. And we have a standardized way of doing that. It's called percent error, and it looks like this. Percent error is given by error divided by the correct number. If you happen to know it, multiplied by 100. And when you do that, you'll get an answer that is a percent. So let's do that. We have 0.01611 divided by 13 times 100. And the answer is 0.124. And don't forget to say percent, otherwise you're not being correct about it. Now, a way to visualize how good or how bad this is just to think, you know, I'm trying to save up $1, and I'm not quite there. Let's just say I'm short. Well, how short are you? 1% error would mean you were 1 penny short. 2% error would be 2 pennies short. A 0.1% error means you've got 99 cents and you almost have 9/10 of the last penny that you need to get to your dollar. So you're about 1/10 of a penny away from $1. That's a way of visualizing what this error is all about. Anyway, that concludes this exercise with Euler Solution. If you're my student, I miss you. If you're not my student, you're just out there on the internet, I hope you enjoyed this and learned something. And be sure to watch some of the other videos and have a good day.